Okay, hi, we're back again. Unfortunately, we do this every 15 minutes because that's what YouTube does. So we're back with an example. We're back to asymptotes, and we're doing rational functions. And the rational function we're dealing with is x squared plus 3 in the numerator and 1 minus x in the denominator. Notice I've turned it around to minus x plus 1 so we could look at the n and the m's. Notice the n here is going to be 2, which is the power of the first term in the numerator, and the m is going to be 1, which is the power of the first term in the denominator. So in this case, n is greater than m. So with our rules, there are no horizontal asymptotes. For the vertical asymptotes, we set the denominator equal to 0. Minus x plus 1, we get minus x is minus 1, so x equals 1 is your vertical asymptote. Now, when I graph this, I got something like this. Okay, once again, the same actually the same window. So it's the same window. Y window, you can just do a standard window between plus or minus 10. X window between plus or minus 10. So what you're going to get here is you have no horizontal asymptotes, so you would have no horizontal line. But you have a vertical asymptote at 1, which is around over here. So I'm going to draw a vertical line, since it's a vertical asymptote, over here. So that defines where the curve will approach. And now if we put it into our graphing calculator, we get something like this. And then we get something which is a little bit weird, but it's got a really bias. It looks something like that. And of course, this approaches. Notice as you can see, as we get here, as x goes this way, y approaches minus infinity here. And as x goes this way, well, y approaches plus infinity there, and that's the definition of a horizontal asymptote. Let's do another example. I'm going to have to erase this. I don't have a lot of room on this board, unfortunately. And it's a little weird. It's vertical rather than horizontally oriented. So years ago, when I was young enough to do yoga, I could probably stand on my head and write upside down. Okay? Probably getting the same solutions, hopefully. So, example 3. We have this, f of x equals 10x divided by x squared plus 9. And if we define n and m here, you notice n equals 1, that's this power, and m equals 2. So that'll help us later on. So first we want to find the vertical asymptotes. So we set the denominator equal to 0, and you're going to find out something weird happens here. If I take the square root, x equals the square root plus or minus the square root of minus 9. Now, if you remember how we can write imaginary numbers, I can write this as the square root of 9 and the square root of minus 1. Notice you could multiply radicals together and the radical disappear. That's the same thing. So the square root of 9 is 3. The square root of minus 1, of course, is I. Now what do we get here? It's an imaginary number. There are no asymptotes. The number doesn't exist on the graph. So in this case, we would have no vertical asymptotes since x is imaginary. It is not a root or anything approaching what's on that graph. So we might expect this graph, when we draw it, to have some different types of behavior. But let's look at the horizontal asymptotes. And notice we have here that n is less than m. Go back to your rules on page 2, okay? And you notice that when n is less than m, the horizontal asymptotes is at y equals 0. So that's right on the x-axis. So the asymptote is the x-axis. Sorry, that's as opposed to the x-allies. I've been watching too many World War II films. X, fx. Now, this is our graph. Sorry. So we're going to put our graph down here. And where's our asymptote? Right on the x-axis. And this is where y equals 0. So that's your horizontal asymptote. So now when I do this one, I have to be careful. My window is going to change. And I'll give you the window in a minute. As soon as, if you flip to page 4, you'll see that this window is minus 1, minus 2. So you can use a standard window for your y. But here, because of the 10 in here, you're going to have to go 15 to 30. So your x window would be, I would do minus 40 to plus 40. For your x window, x min, I would do minus 40, and x max, plus 40. All right, so what does this look like? Well, this starts, actually, this crosses the 0 axis, and it goes something like this. It comes down to 2, and it goes like this, and it goes like this. Notice this is supposed to be like this. As x approaches plus infinity, what happens? Y approaches 0, okay? As x approaches minus infinity, going in this direction, y approaches 0. I'm sorry, 0. Z0 is the asymptote. So, but it never reaches it. That's the idea of asymptotes. Now, as we said before, we might be worried the fact that since we're doing max min here, if we have asymptotes, can we ever have a max min? Well, I think this example sort of gives it away. What you see here, a minimum and a max, and you might be worried if our techniques that I taught you apply to this, and they certainly do. Okay, as long as we stay away from the endpoints here, you're okay. So what I'm going to do is solve a rational function, get min-max, and see what that means in terms of the asymptotes. So I can erase this because you guys have all this. This is all in your notes. Notice I'm really constrained. I cannot maybe do one problem per erasure. So bear with me here. This is the first time I've done this without an audience. I do have an audience of one, my videographer.
Hello.
Greg Mattis, who also is a math professor. So if he finds me making any mistakes, he is going to pretend he's a student and say, "Hey, Dr. Mirabile, you messed up there."
So okay. I really have to pay attention.
Just like you guys. Okay, so anyway, I'm going to talk about this is rational. No, this is not a good pen. I'm sorry. Well, let me go back to the black. So Oh, it's been out too long in the sun. Okay. Now let me try blue. Let's try them all. Yes, great. This is rational functions in business. Some people might claim that there's no rationality in business, but that's only in some other systems, which I won't mention because I get in trouble. Okay. But the system begins with an S. Okay. I have 5,000 x plus 125,000 over x with the constraint that x must be greater than 0. So notice x cannot be 0 here. Something happens around 0, which we'll see when we graph this. So let's define these terms. C of x is simply the cost in dollars. There's no... And x is, in this case, the number of machines used in production. Obviously, this is some sort of manufacturing place. So what do we want to find? First thing is find all asymptotes. So let's, now you're saying, wait a minute, Dr. Mirabile, this doesn't look like everything that we had before. I don't have a numerator over a denominator. Well, I have to find here the LCD. Now, that's not a Ford car, it's the least common denominator. So, what will be the least common denominator? Well, let me put this over 1. So the least common denominator is when 1 times x is going to be x. So 1 times x is x. X times 5,000 is 5,000 x squared. X times 1 gives you x. Multiply the 1 times 120. Yes. Oh, 2. Okay. 125,000. And there's my rational function denominator. So here we have m equals 2 and n equals 1. All right, now what about my vertical asymptotes? Well, notice my vertical asymptote, I set this equals 0. But what did I say? This cannot be 0. So is this a vertical asymptote? Well, let's assume that it is right now. So we'll say that this is your vertical asymptote, and let's see what its behavior here. And horizontal asymptote, I have n is less than, n is less than m. So where is my vertical, horizontal asymptotes? I made a mistake here. This is our n factor, and that's our m. So n, don't forget, n in the numerator, n for numerator, and m equals 1, almost finished. So then here we have here, n is greater than m, which means we have no horizontal asymptotes. Okay, and we will continue. We have to stop right now, and we'll continue with the last part of this first lecture. We're taking a break.